In Chapter 7, we are going to look at estimating things about a population. In Chapter 6, we pretended that we knew true population parameters. We pretended that we knew the mean for a population, or we pretended to know that we knew the standard deviation for a population. This chapter focuses on the use of sample data to go ahead and estimate a population parameter. This chapter is a realistic approach. We're going to begin with sample data and then ask questions about the actual population. We're going to be focusing on samples since populations in general are very hard to deal with. We cannot get every item in a population easily, and that's the reason why we use samples so often and the reason why statistics is so important. Does a sample perfectly reflect a population in every single case? Well, if you want to think about that, do you perfectly reflect all individuals at Burbank High School? And the answer to that is no, you do not. So when we look at a sample, if 1/6 of the sample has blonde hair, can we say that 1/6 of our whole population has blonde hair? No, we don't know how well the point estimate or that value is at representing our sample. And so it could be accurate or it could be way off. And so we have to have a way to deal with that. And today we're going to start in on a way to deal with that. Point estimate is our first vocabulary word. So a point estimate is going to be a single value that is used to approximate a population parameter. Your point estimate could be a proportion, it could be a mean, it could be a standard deviation. It is the single best guess for the value of a population parameter. The best guess that we would have for a population proportion would be what they call p-hat, or the probability for a sample. So p-hat is going to be the number of successes divided by the number of trials. This was like our experimental probability back in the probability chapter. It is the best estimate we have for our population proportion. Just like the best guess for a population mean, mu, is going to be x bar. However, they are almost certainly going to be a little bit off. So, as a result, we create what we call a confidence interval. And a confidence interval is going to be a range or an interval of values that are used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI, and it is sometimes called an interval estimate. A little note about it, a confidence interval is associated with a confidence level. The confidence level gives us the success rate of the procedure. That confidence level is going to tell us how successful the procedure that was used to construct our confidence interval was. The way that we will write a confidence interval is p hat plus or minus e, where e is that confidence level, or p hat minus e is less than p, which is less than p hat plus e. Or we can say p hat minus e, comma, p hat plus e. And this will make more sense when we actually look at an example and see how it's used. All a confidence interval really is an interval of those plausible values, and E is going to be our margin of error or the possible error. Confidence level is the probability, or 1 minus alpha, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called the degree of confidence or the confidence coefficient. So you might see those written in other textbooks or in other ways. The most common ones are 90%, 95%, and 99%. Critical value. Critical value is the number on the borderline that separates simple statistics that are likely to occur from those that are unlikely to occur. And for margin of error, it is the maximum likely difference between the observed sample proportion and the true value of the population proportion, sometimes called the maximum error of the estimate. In this section, we are going to be looking specifically at proportions, but this can also be applied to means, which we will see in later sections. And for the margin of error, the symbol is E. Our margin of error is essentially how far we expect the sample statistic to vary from the population parameter at most. We know that there is going to be variability in sample statistic results. So we create this interval so that we have some wiggle room. And we deal with a range of values in Chapter 7 rather than a specific value, so that we're somewhat confident that our population will be within that specific interval. Example number 1 says, a news team asks 100 randomly selected zombies what type of brain they like to eat. 70 of them say that they prefer female brains. Find the best estimate you can of the proportion of all zombies who prefer female brains. Well, the only thing we know is we have this sample. So we can give our point estimate, or in this case, it will be p hat, where p hat is equal to the number of successes divided by the number of trials. Here, the number of successes is 70, since 70 of them said they prefer female brains, out of the 100. Or we could say p hat is equal to 0.7. As a side note, p hat is going to be the sample proportion. Just how x bar is our sample mean, p hat is the way that we'd write a sample proportion. The proportion you came up with from example 1 is our point estimate. How good of an estimate is it? We aren't really all that sure. We know that it is a relatively okay estimate. We saw in the last chapter that proportions are unbiased estimators of our population. So we could say something like the estimate is probably not equivalent to the population proportion, and there definitely is some error since we are using a sample. However, it is the best estimate that we have. We don't have much else to go off of. How confident would you be that the actual population proportion of zombies that prefer female brains is between 0.68 and 0.72? The smaller your interval is, the less confident we can be that it's going to fall within that range. 0.7 does fall in this range. However, small intervals are going to make it us less confident. Larger intervals are going to make us more confident. We could say, since it is a relatively small interval, we cannot be highly confident. If our interval was the entire range from 0 to 1 probability values, we could be 100% confident that the population proportion lies in that range, since it would cover all probabilities. So the larger our interval is, the more confident we can be. However, the smaller our interval is, the more accurate we have. So we have to kind of battle between this: how confident do we want to be, and how accurate do we want our information to be. I'm going to make a note here that says the more confident you want to be, the bigger your interval needs to be. And the next part says, how confident would you be that the actual population proportion of zombies that prefer female brains is between 0.5 and 0.9? This is a larger interval. We will be more confident than the previous interval because it is a larger interval. Example number 2, the 95% confidence interval estimate of the population proportion P is 0.610 is less than P, which is less than 0.790. Interpret this in the context to example 1. We will learn how to find our confidence interval, but for today, we're just going to understand how to talk about a confidence interval. So this essentially says that we are 95% confident that this interval from 0.610 to 0.790 actually does contain the true value of the population proportion for P. Therefore, the proportion of zombies who prefer female brains, we're 95% confident it's between 0.610 and 0.790. All right, we are 95% confident that the interval from 0.610 to 0.790 actually does contain the true value of the population proportion P. And notice we use P for the population proportion, and we use P hat for our sample proportion. Example 3, use the confidence interval given in example 2 to find the margin of error. Our margin of error, we said, is the maximum likely difference between the observed sample proportion and the true value of the population proportion. Our interval could be above and below our value. Our value is going to be somewhere in between. We're going to assume that it is exactly in the center. So the way to find a margin of error, if you know the interval, is to take the upper value minus the lower value and then divide by 2. Essentially, we are averaging the ends of our interval. We're going to take 0.790 minus 0.610 and divide it by 2. We end up with 0.09. And the reason for that is P hat plus E is the upper confidence limit. And P hat minus E is our lower confidence limit. Since we have P hat plus E and P hat minus E for our upper and lower confidence limits, if we want to find the margin of error, which was being added and subtracted to our P hat or our sample proportion, we just have to find half of that distance, essentially. Some other confidence intervals from example number 2. If we're 95% confidence, our confidence interval is from 0.61 to 0.79. Our lower confidence limit is 0.61. Our upper confidence limit is 0.79. Our P hat, which is going to be directly in the middle, or in this case, we had found it to be 0.7 in the very first part of example 1. And our margin of error we found up here to be 0.09. If we're 90% confident, notice that our confidence interval is now slightly larger. Our lower confidence limit is 0.62. Our upper confidence limit is 0.78. Our P hat remains the same. The way to find the margin of error would either be to subtract these two and divide by 2, or since we know P hat, it's how far are we away from each of the ends, essentially. So 0.78 minus 0.62 divided by 2 leaves us with 0.08. And then 50% confidence interval. Notice it got even larger. Our lower limit is 0.67. Our upper limit is 0.73. And our margin of error, we need to subtract those. 0.73 minus 0.67 and divide by 2. We get 0.03. Another way to look at it is how far away is 0.7 from 0.73? It's also 0.03. What does 90% confident actually mean? What it means is if we were to continually take sample after sample after sample after sample and calculate many different intervals, then about 90% of those intervals will contain the actual value from the population, whether that is the proportion, the mean, or the standard deviation. I'm going to write that down. So if we were to take many samples and calculate many confidence intervals, one for each sample, 90% of the intervals will contain the true population proportion. Essentially, we would have to be taking a bunch of samples and finding a confidence interval for each sample. Then 90% of those intervals will contain the actual population proportion. As we talked about before, while a 50% confidence interval is narrow or more specific, it likely does not contain the true population proportion. The 99.999% confidence interval is going to be very wide. In this example, it would be 0.49758 to 0.90242. And while this interval is very wide and not very specific, we're going to be a lot more confident that it contains the true population proportion. Example 5 is another example to help us go through and see how this plays out. So it says a large company is concerned that many of its employees are in poor physical condition, which can result in decreased productivity. To determine how many steps each employee takes per day on average, the company provides a pedometer to 50 randomly selected employees to use for one 24-hour period. After collecting the data, the company statistician reports a 95% confidence interval of the 4,547 steps to 8,473 steps. The first part is to interpret this confidence level. What is this saying? Well, it is saying that if we take many samples, and calculate many intervals, about 95% of our intervals will contain or will capture or contain the true mean number of steps per day for employees. In our zombie example, we were using proportion. Here we're talking about mean. Notice that you can use either the proportion or the mean and create an interval. Part B, interpret the confidence interval. So we are 95% confident that the interval from 4,547 to 8,473 contains the true mean number of steps per day for employees. So interpreting the confidence level and the confidence interval are about the same. There's not too much difference between those two. For part C, it says what is the point estimate that was used to create the interval and what is the margin of error. The point estimate in this case is going to be X bar. Since we were dealing with means, our point estimate is going to be the mean of our sample. And it is found in the middle of our interval. The way that we find that is we are going to average halfway in between. So we're going to take our 4,547 steps and add it to 8,473 steps, then divide by 2. And that ends up being 6,510 steps per day. To find the margin of error, there's different ways that we could do it. The first way is that we could subtract the highest or the upper level minus the lower and divide by 2. Which gives us 1,963. Or we could take 6,510 and subtract it from 8,473, which will give us also 1,963. Since our point estimate is plus or minus the margin of error. For part D, it says, recent guidelines suggest that people aim for 10,000 steps per day. Is there convincing evidence that the employees of this company are not meeting the guideline on average? Well, the first thing to think about is 10,000 included on our interval. And the answer to that is no, it is not included. So therefore, we wouldn't consider 10,000 to be a possible value for our mean of the population. We can conclude that there is convincing evidence that the employees are not meeting this guideline on average. Since 10,000 is not in that 95% confidence interval, so therefore employees are not taking 10,000 steps per day on average. Example 6, how can we reduce the margin of error in a confidence interval? The way that we can reduce, I'm going to call this A. So we can reduce the margin of error by either reducing the confidence level or by increasing the sample size. So if we reduce our confidence level, if we go from a 99% confidence level down to a 90% confidence level, then that is going to reduce our margin of error. Another way is if we increase our sample size, because increasing our sample size is getting us closer to the actual size of our population. For part B, it says, why do we want a small margin of error? And for the second part here, I'm going to call it B. And we want a small margin of error because we want more precise estimates. And then the last part here says, are there any drawbacks to the actions? So are there any drawbacks to reducing either the confidence level or increasing the sample size? So the drawbacks to reducing the confidence level are that we are less likely to capture the true population values, either mean or proportion, and increasing the sample size results in higher costs. In our examples, we have seen how to interpret a confidence level and also how to find a confidence level if we are given the margin of error, and also how to find a point estimate if we're given our margin of error. And we've also talked about what it means to be 90% confident or 50% confidence, etc. The reason why we are putting together a confidence interval is because we don't know how accurate the point estimate is. We take a sample from our population and we get a value. And we know that that value is a relatively good estimate of our population, but we don't know much about our population. Therefore, we have to use confidence intervals. And we create confidence intervals so that we have a range of numbers that we know how confident we are that our actual population value will fall in that interval. Our point estimate comes from a limited number of trials. We don't know how good or how bad it is. It's not a complete picture of our actual population. The next step, now that we have some understanding of confidence intervals, is actually going through and creating a confidence interval. And when we are going to be creating a confidence interval, we need what they call a critical value. And this is going to combine our ideas from chapter 5 and chapter 6. It's bringing a lot of stuff together here. So a critical value is a z-score that separates the likely region from the unlikely region. Likely being the region that our confidence interval is based on. We have to find a range of values based on how confident we want to be. So if we want to be 95% confident, we need to know what that area is. From chapter 6, we know that in between two values will lie 95% of our data. So that is our confidence level. And we need to find what are the z-scores that cut off this area, specifically those we consider them to be our critical values. Our confidence level is going to be 1 minus alpha, or the complement of alpha. So what is alpha? Alpha is the area that we don't want. So our alpha are these outer sides here. However, notice there's two of them, and because of symmetry, they're going to be equal to each other. The whole sum of them is alpha, so therefore each side is going to be alpha cut in half. So here we're trying to come up with 95% confidence level. If we wanted to create a 95% confidence interval, we would be finding some range that is based on how confident we want to be. We want to be 95% confident, and we need the values for that range. We are using the fact that we want a certain level of confidence, and we're going to find our z-score. And then using that z-score, it's going to help us to make our range for our point estimate. So we need to find out what that z is. And more specifically, it's z sub alpha divided by 2, where this one is negative and then that right one is positive. So if we find one of them, we know we can find the other. So for a 95% confidence level, if we want to be 95% confident, the shaded area is going to be 0.95. So therefore, we need to find this area. If we can find this area in the table, then it'll tell us what our z is. And we've done that often in chapter 6. So if we take our alpha, what is alpha in this case? Well, our alpha is going to be 1 minus 0.95, or the complement of our confidence level. And so alpha in this case is 0.05. So there's 0.05 in each of these two ends. And then we have to divide that by 2. So alpha divided by 2 is 0.025. From there, we have to take our z table, and we are going to have to find 0.025, or the closest thing to 0.025 in our table. And we see right here, 0.025 is a z-score of negative 1.96. So our z values are going to be negative 1.96, and then also positive 1.96. And the reason why is because this is symmetric. So on either side, it's going to be exactly the same. We don't use the negative one as a critical value. We always use the positive one. So there's the one that we would use if we said we were 95% confident. We can do the exact same thing to find 90% confidence and then also 99% confidence. We need to find that z-score. where this area is 0.90. And so we need to figure out, okay, what are these two areas? So if alpha is 1 minus 0.90, or if our alpha is 0.1, then half of that is 0.05. So this little piece here is going to be 0.05, and this little piece here is going to be 0.05. So again, we go to our z-score table, and we have to find 0.05 in our table. We have 0.0505 and 0.0495. Notice that 0.05 is exactly halfway in between these two z values. So what we're going to have to do is we're actually going to have to average these two. So this is negative 1.64 and negative 1.65. I'm going to take negative 1.64 and negative 1.65, average it, and I end up with negative 1.645. So therefore, our z in this case is going to be 1.645. And then for 99% confidence, the same thing. We just have a wider interval here where this is 0.99. And then this little piece and this little piece are going to be our alpha divided by 2. So in this one, our alpha is 0.01. So alpha divided by 2 is going to be 0.005. And we find 0.005 in our table. It is exactly halfway between negative 2.57 and 2.58. So therefore, we average those, which gives us negative 2.575. So our z is going to be 2.575. And notice, right, one side is negative, this one's negative, and this one over here is positive. We're only going to end up using the positive one, but I use the negative one because it's the easier one to find since the table gives us values to the left. Now, 90, 95, and 99% confidence are the most commonly used confidence levels. More than likely, you're going to be dealing with problems that have one of these confidence levels. And so you can just use these values, and if you even look at the standard normal probability table, they call it table A from the textbook, it has these written down at the top or the bottom of it. I don't remember which one. And so you don't have to actually find them. However, if you don't have 90, 95, or 99% confidence level, then you will need to find the z-score on your own. So why do we need to find a confidence level? Why do we need to find a critical value? Essentially, what we're doing is we're basing our confidence interval, or this range, off of our point estimate. And then if we want to be 90% confident, we know that it's going to be somewhere between the range. Since this range is based on a certain level of confidence, we know that we will be certain that our value will fall somewhere in that range. So essentially, we're working backwards. We are building our interval based on how confident we want to be. And we'll actually look at some examples of making confidence levels in the second part of this section.